the first thing that we should try to do is to convert the equation of the plane from the Cartesian form to the dot product form. And the equation of plane P will be r dot, the normal vector will be 3 minus 4 minus 1. So 3 minus 4 minus 1, and this is equal to minus 7. We will also want to convert the equation of the line from the Cartesian form to the vector form. So I'm going to be letting x minus 9 divided by a to be equal to lambda, which means that x is going to be equal to 9 plus lambda a. I'm going to let y plus 5 over b to be equal to lambda. So y is equal to minus 5 plus lambda b. And as for z minus 2, I'll let this be equal to lambda. So z is just simply going to be 2 plus lambda. But of course, this can be done through mental sum. So if you're able to do that, you probably can quote the equation of the line directly. It is going to be equal to x is 9, y is minus 5 here, and z is equal to 2 here. Keeping this as the first vector plus lambda of a, b, and 1. And we want to check whether this line is parallel to the plane. So when a line is parallel to the plane, so let's say this is L and this is P. If the line is parallel to the plane, that means the normal vector to the plane, which is 90 degrees to the plane, in this case here, it is vector 3 minus 4 minus 1. This must also be perpendicular to the line. And the line is parallel to the vector A, B, 1. So since they are perpendicular to each other, we can do a dot product. We will take A, B, 1. This dot 3 minus 4 minus 1. And this should be equal to 0 since these two are perpendicular to each other. So we have 3a minus 4b minus 1 is equal to 0. Or you can definitely make a and b to be the unknowns on the left hand side here. So this is equal to 1. We are now given that a is equal to 2 and b is equal to minus 2, which means that the equation of the line L will be now 9 minus 5, 2 plus lambda of 2 minus 2, 1. And if I were to substitute the values of a and b into the relationship that we have found in part 1, we know it is not going to satisfy that relationship. That means that for whatever that we are trying to analyze here, the line L is not going to be parallel to the plane P. And this is the reason why it is possible for the question to mention about the intersection between this line and the plane. Because when the line and the planes are not parallel to each other, they will be intersecting at a point. And I'm going to call this point B. And I'm going to try to find the position vector of this point B. So to find this position vector, what I'm going to do is to solve this as a pair of simultaneous equations. Because at the point B, they are going to be sharing the same R. So I'm going to substitute this entire expression here into the R of P with an attempt to solve for the specific value of lambda. Which means that I'm going to take 9 minus 5, 2 plus lambda of 2 minus 2, 1. And I'm going to put this into the R of the equation of the line, equation of the plane P. So this dot 3 minus 4 minus 1, this is equal to minus 7. I'm going to make this into one single column vector. So 9 plus 2 lambda. And we have a minus 5 minus 2 lambda and 2 plus lambda. So this is the column vector dot 3 minus 4 minus 1. This is equal to minus 7. So expanding this dot product, 3 times 9, 27, then plus 6 lambda plus 20 plus 8 lambda minus 2 minus lambda. This is equal to minus 7. If I were to put all the lambdas on one side only, we have a 13 lambda, and on the other side is going to be a minus 52. This helps me to solve for the value of lambda, and this is equal to minus 4. So I'm going to substitute this lambda back into here, which will then help us to find the position vector of the intersection between the line and the plane. So OB is going to be equal to 9 minus 5, 2 plus lambda, which we have just found out to be minus 4. Then here it is going to be equal to 2 minus 2, 1. So the position vector of the point of intersection between the line L and the plane P is going to be equal to 1, 3, minus 2. Now part B, we are looking at the point A, and the point A was given to us with the position vector as 9 minus 5, 2, which means that the coordinates of A will be 9 minus 5, 2. And we want to find the position vector of the foot of the perpendicular from A to the plane P. So the foot of the perpendicular, we are talking about this point here, and I'm going to call this point here F. So since it's the foot of the perpendicular, I know AF is going to be perpendicular to the plane P. And to find the position vector of F, I'm going to use a strategy that I discussed on the Achevas TV theory outline. So to do that, we will first form the equation of a line that passes through AF. So for this line, R is going to be equal to, it passes through this point A. So 9 minus 5, 2 will be here. Then plus, since we have already used lambda for the line L, I'm going to use beta. Beta of a direction that is going to be parallel to AF. And the direction that is parallel to AF is going to be parallel to the normal to the plane P. So the normal to the plane P, which was 3 minus 4 minus 1, I am going to make use of it here. So 3 minus 4 minus 1. And by forming the equation of this line, we can use the same method as what we have used in part A to find the intersection between a line and a plane, which means that at the point F, I'm going to take this and substitute it into P. Okay, I'm going to substitute this into P. So it will be once again 9 minus 5, 2 plus beta of 3 minus 4 minus 1. I am putting this into the plane P's equation. So 3 minus 4 minus 1, this is equal to minus 7. And this, making it into one single column vector, we have this, then minus 5 minus 4 beta, and a 2 minus beta. So I'll take this dot 3 minus 4 minus 1. This is equal to minus 7. So with this, expanding it, it is going to be 3 times 9, 27, plus 9 beta, plus 20, plus 16 beta, then minus 2 plus beta. This is equal to minus 7. This will help me to find the value for beta, because from here, we know that we are going to be getting a 26 beta. This is equal to minus 52. So beta here is equal to minus 2. So substituting this beta back into the equation of the line that passes through AF will give me the position vector of the foot of the perpendicular. So OF is going to be equal to 9 minus 5, 2 plus beta, which is minus 2. So minus 2 of 3 minus 4 minus 1. So OF is equal to 3, 3, 4. And we're going to make use of the position vector of F to find the shortest possible distance from A to the plane P. So it is going to be modulus of AF. So let's try to find the vector AF, which is going to be vector OF, 3, 3, 4, minus away the position vector of A, which is 9 minus 5, 2. So vector AF is equal to minus 6, 8, 2. So the shortest possible distance that the question is asking for, shortest distance, is going to be modulus of AF, which is going to be square root of minus 6 square plus 8 square plus 2 square. So my final answer here is going to be square root of 104. In the last part here, we are supposed to find the angle that is between the line L and the plane P. So it is going to be this angle over here. We are supposed to find angle ABF. And if I were to try to piece all the information that we have found so far together, this is the diagram that we have gotten. And to find this, we can just make use of the right angle triangle that we see here. The one more information that I probably need to calculate now in order for me to make use of this right angle triangle is the length of AB. So let's do that. Let's find vector AB, which is OB minus OA. So it will be 1, 3, minus 2, minus 9, minus 5, 2. And AB will have a vector minus 8, 8, and minus 4. So now we can find the length of AB. It is going to be square root of minus 8 square plus 8 square plus minus 4 square. And this is equal to square root of 144, so it is equal to 12. And now we can make use of this triangle, this right angled triangle. It is sine of the angle ABF. This is equal to opposite over the hypotenuse. It is going to be square root of 104, the opposite, over the hypotenuse, which is AB, divided by 12. So the required angle, let me write it down here, the required angle, which is the angle between the line L and P, is this angle ABF, and it can be calculated by doing a sine inverse of square root of 104 divided by 12. So this angle is equal to 58.2 degrees.